Okay, so now we are ready to get some payoff from all the hard work that we've done with the matrix formulation of the linear model. We are now going to learn how we can define contrast coding in arbitrarily complicated designs, and how we can use contrast coding to answer our research question directly. Okay, so I'm going to focus on contrast coding first for two condition experiments. These are the cases that we have studied in the introduction to linear models, where I have only subject and object relatives. So that's the kind of situation I'm talking about here. And then I will talk about three condition designs where I have, let's say, condition A, B, and C, and I want to do a pairwise comparison, let's say, between A and B and B and C, right? Notice that if you have three conditions, you only need to do two comparisons. Like, there's no point in comparing A with B, B with C, and then A with C, right? So one often sees people doing this with pairwise t-tests, but for three conditions, you only need to do two comparisons, and in fact, you should do only two comparisons, because the third one is redundant. And then after we've looked at three condition designs, we will look at standard 2x2 factorial design. So here I will introduce the kind of contrast coding that is used for such designs. Okay. So the simplest kind of experiment you can run is one with just two conditions, so like the subject and object relative clause cases. So I'm calling that a 1x2 factorial design. It's kind of an exaggeration, because I mean, it's just two conditions. Seems like overkill to call it factorial, but sure, you can do that, right? Similarly, you can call a three condition design a 1x3 factorial design. The reason you have 1x2 and 1x3 is the following, right? So you can think of a factor f with two levels. So this is one factor with two levels, and that's why they say 1x2, right? Similarly, you can have a three condition design where you would have three levels, right? So then it would be a 1x3 design. So that's why this terminology, right? Now the most common kind of experiment that we generally do in psychology and linguistics, I think it's fair to say, would be something like a 2x2 factorial design. Certainly this is very common in my lab. We often do such studies. You can see such a 2x2 design in the following way, right? So there are two factors now. So it's not one, but there are two factors, each of which has two levels. Okay, so that's why we call it a 2x2 design. So we can call these condition levels F1A, F1B, whatever convention you have, it doesn't really matter. But you can label these as unique labels, F2A, F2B, and like often when we're practically running experiments, what we will often do is we have a 2x2 design and we will label the conditions A, B, C, and D in the item list, when we're actually running the experiment. What that means is that in your data frame, you will have a column called condition or something that can have the values A, B, C, and D, right? But then if you want to label the different levels of these factors, you will have to create some way of talking about the two factor levels, F1 and F2, let's say, and then you'll have to talk about the level 1 and level 2 of these factors, right? So F1, 1, F1, 2. So this factor A and B actually belongs to level 1. So how would you represent, the question is, how would you represent these conditions C and D, which actually belong to the other factor, in this column which represents factor 1, right? That's an interesting question now that you'll have to think about. Okay, so the point is that this is just a digression on the data frame that you're going to have, where you will have labels for conditions A, B, C, and D. Okay, so we'll look at an example later, and you'll see how one implements all this. Okay. All right. So you can have more complex designs. So sometimes a 2x2 factorial design can be seen as a 1x4 factorial design with one factor with 4 levels. That can also be, so you can have a situation like this, one factor with 4 levels. So it's really what the basic underlying question is that you're trying to answer, right? So you can have a situation where you are just manipulating the length of let's say a subject-verb dependency. So you can have short, long, longer, and even longer. So that's a 1x4 design, right? So what the underlying design is actually a function of your research question, right? Now you can also have much more complex designs, like a 2x3 factorial design, 2 factor levels with two factors with each level having each factor having 3 levels. Or you can have even a 2x2x2 design, so 3 factors each with 2 levels, and you can go completely crazy at this point and have, I don't know, like 180 different conditions or something. But my advice to you is to generally, as a student and even as an advanced researcher, my advice is to always try to keep your design as simple as possible. And generally I don't really like it when I'm presented with an experiment with a 2x2x2 factorial design. As you will see in some of the exercises I'll give you, the analysis becomes nightmarishly complex and your life actually becomes difficult as a researcher when you're trying to answer too many questions in one experiment. Okay, so I like to keep it simple. So in this lecture I'm going to keep it up to 2x2 and not go beyond that. As I've said here, my advice to you is to keep it simple in your own research. So this is practical advice now. And when you are ever forced to go beyond factorial designs, and sometimes my students do end up with 2x2x2 designs, and recently we are struggling with an experiment with 2x2x2x2, and we are paying the price as usual, so of complexity. When you do a overly complex experiment, then you're going to pay the price down the road when you set up your contrast coding and try to report the results. Okay, so you might as well be conservative at the moment of designing the experiment and stick to a simple design. So I mean, the reason that people do complicated 2x2x2x2 designs or something like that is that they want to answer a range of questions. My advice to you is, if you have the time, either separate your experiments into multiple ones so that you can answer each set of questions one by one, or become more humble about what you can do in a, let's say, a PhD period where you don't have that much money or time, and try not to answer everything in one shot. Okay, it's a radical idea to try to answer what you can instead of trying to go beyond what the statistics can do for you, right? All right, so it has always been a struggle for me with my students. When they're starting out, they want to design an experiment, but they haven't really thought about what their hypotheses are, right? And in fact, when I ask them such a question, they don't even know what my question is about, right? So it's a very common mistake to start without any clear hypotheses. And in fact, that's how I did my PhD at Ohio State, right? I had no idea what my real question was until I started analyzing the data. It's a very common situation. And so what happens is that after the data come in, we start speculating about what we might want to know, and sometimes our research question changes completely based on the pattern that we have seen and so on. Now, this is not a very good way to proceed, because this leads to what's called p-value hacking and something else called the garden of forking paths. So really, there are multiple possible analyses you can do. Once you have the data set with you, you will see all kinds of patterns that look like something fantastic is happening. And as a result of that speculation, that post hoc speculation, you can go down many different paths and come up with many different stories, based on the data. And in fact, you will often see when you're working on a research problem, you start thinking in terms of what story you're telling, and the storytelling can get out of control if you are relying on looking at the patterns in the data and then deciding what the analysis should look like. So a better way is to develop what one can call an analysis plan in advance of collecting any data. You're just at the design stage. What you do is you set up your analysis using simulated data, and in the next lectures I'll show you how to do this, and then you actually do the full analysis on the simulated data, and you're ready with your hypothesis in advance. When the data now come in, you just replace the simulated data with the real data and finish your analysis. So that is something called so these are a priori comparisons, or analyses that you can define before you've seen the data, right? So this forces you to commit to a research question before you see the data, and this prevents you from speculatively p-hacking your data to get some story out of it. Alright, so one tool that we'll talk about towards the end of this course is pre-registration. So this is a way to timestamp your predictions about what you think will happen in the experiment, and then you put this up on some website like osf.io or aspredicted.org, and these websites allow you to pre-register your analysis and to prove that you had actually predicted a particular analysis before you even collect the data. So this is a very long digression before we get into the action in this paper, so let me move on. But I just want to give you the background for why contrast coding is such an important thing. It's important because it allows you to prepare in advance for your research, for your data analysis. Okay, so in this particular lecture we are going to simulate data, but we're going to simulate it using a built-in function that I have provided in the functions directory on the GitHub repository or the OSF repository for this for the materials for this course. Later on we will simulate our data by hand, okay, but right now we are using a built-in function. So what this function does is it allows you to generate within or between subjects data, and what you define, for example, if you have a two-condition experiment that you want to simulate, you decide on the means of the two conditions. You save that in the M vector. We are going to set a seed that ensures that if we repeatedly run this, generate this simulated data, we will get exactly the same random numbers again and again, right? So we're just controlling the randomization of the numbers by setting a seed here. So what you do is you use the usage of this function is this is called mixed design, and so we are defining here 2 between subjects factors, no within subjects factors, 5 data points in each condition. Okay, the M vector of means is given here, the standard deviation of all the conditions here, the 2 conditions are defined here, and here we are specifying that we want the data in long format, not wide format. If you remember, I explained this earlier, right? So this is my simulated data, and this is what it looks like now. I've got a column, I've got a subject column, right? ID column is the subject column. There are 10 subjects because there are 5 data points in each condition, and there are 2 conditions, right? And you can see with the xtabs function that the conditions are labeled A1 and A2, right? For a between subjects factor called factor A, right? B sub A is factor, a between factor that is called A, and each of the levels in the 2 factors are called A1 and A2. And you can see from the xtabs function that the first 5 subjects see condition A and the last 5 subjects see condition B, right? So this xtabs function helps you check that you got you have designed the experiment correctly, right? You've set up your data correctly. You can also generate within subjects data with the mixed design package by changing the following things, right? So what you have to do is, instead of B, you say W equal to 2, W for within, and now you specify that there is no between subjects factor anymore. We have 5 data points for each subject, and we use the M vector that we had created a couple of slides ago, right? This matrix has 2 rows and 1 column, right? So basically this matrix will look like 0.4, right? It'll be a 2 by 1 matrix, right? So for for a within subject specification, you have to transform this. You have to transform this matrix and make it into a 1 by 2 matrix, right? So that's what I've done here. You can see that this is just the way the mixed design package is written. It's meant to be a convenience such that if you have a 2 by 1 column, that marks the between subjects means, and the row wise mean specifications will, I'm about to sneeze. Yeah, the row-wise specifications tell you the within subjects means, right? So this is meant to be a convenience such that you can actually define complicated designs with both between and within subjects designs factors, right? This is something that I would never do in my research. I want to keep my experiments simple. I'm talking about practical research now, okay? I don't have such complex designs, but it's possible to have such things, and sometimes they're necessary. So this package allows you to simulate that situation. And so that's why I have a transform on the means, because I'm generating within subjects data now, right? And so if I do the xtabs function now, I do indeed see that now I have only 5 subjects, because each of the 5 data points is now coming from the same subject in the 2 conditions, right? So that you can see that here now, that for the 2 levels for the within subjects factor called A, the 2 levels A1 and A2 have 1 data point each from each subject. Okay, so now it's become a within subjects data set. So this is how you can generate the data. Okay, that's pretty straightforward now. But we're going to stick with a between subjects design, because for contrast coding it doesn't matter whether you have between or within subjects designs for understanding how contrast coding works, right, in general. So here we go. Okay, so we have a 2 condition experiment. That's the sim data that I just generated earlier, this thing here, right? I'm talking about this data here. So I have between subjects data called simdat, and I'm renaming the factor level from B sub A, which is an inconvenient label, to F, just for convenience. Okay, you can call it whatever you like, and the levels of this factor have been relabeled to F1 and F2, again just for convenience. Okay, so now my data frame looks like this. I have a subject column, ID column. Here's my dependent variable. This is intended to be this 0.99 etc. is supposed to be in seconds. This is the unit I'm thinking about here. And F is the factor name, and the levels are shown here, right? F1 and F2. Okay, so that's what it looks like. You have another way to look at the data frame using the str function. The structure, I think, is what it stands for. This tells you what the structure of the data frame is. You've got a factor column, which is has 2 levels, and then I have an ID column with 10 levels, and then I have the dependent variable, which is a numerical value. Okay, all right, so I can use some fancy tidyverse type of coding, right? So if you're not familiar with this syntax, I will explain it when we meet over Zoom. But basically what I'm doing is I'm setting up a nice neat table which summarizes the means for each of the 2 conditions, right? So that I've got mean 0.8 for F1 and 0.4 for F2, and I have 5 data points in each of those levels, and the standard deviations are here, and the standard errors have been computed given the standard deviation and the sample size. Okay, so these standard deviations are computed like this: 0.2 divided by the square root of 5. Okay, so that should be 0.0894. all right, and I've also computed the grand mean here, which is what? The grand mean should be 0.6, right? Because I have 0.8, 0.8 plus 0.4 divided by 2 should be 0.6. Okay, all right, so graphically, when you publish papers and you have a 2 condition design, well, it's kind of an exaggeration to draw a figure for 2 conditions, but you could, right? So this is one way to visualize it. So what I've got here is 1 standard error plus minus 1 standard error around the mean for each condition, and this is a very common way to summarize your experiments graphically. Okay, so now we are ready to do our data analysis. Of course, you're familiar with the treatment and some contrasts. I kind of introduced it earlier. So what's happening here is that I'm fitting a linear model with the default contrast coding on the F factor. And so if I look at the output of this model, what I get is I get an intercept and slope, And the question is, what are these intercept and what do these intercept and slope mean? Of course, you already know the answer because we've done treatment and some contrast. The baseline condition here is F1. Therefore, the intercept is telling us the estimated mean for the F1 level, and the slope, which is labeled FF2 here, is telling us the difference between F2 and F1. Okay, so that's why R prints out this FF2 here, because this second level here is supposed to tell you what you're comparing against what. The mean of F2 is being compared with the mean of F1. If I had reordered the factor levels, then what would have happened is that the intercept would reflect the mean of F2, right? And the slope would then reflect the difference between mu F1 and mu F2, and the LM output, when I print this out, it would not show me FF2 like it's showing me here right now, but instead it would show me FF1 because it's telling me what the first mean is that I'm subtracting from. Okay, so that's this factor releveling that I had discussed some lectures ago, right? So you can do that. Anyhow, so the interpretation of the intercept and slope is clear for the treatment contrast, and this is the treatment contrast coding that I mentioned earlier. So the important thing to understand here is that the treatment contrast expresses some null hypotheses for the intercept and for the slope, right? For the slope, it's expressing the null hypothesis that the difference between the two levels of the factor f is 0. And so you can write down the null hypothesis like this. Right, so you could also write the null hypothesis by saying that my null hypothesis is that the slope is 0. That is also correct. But underlyingly, the hypothesis that you're talking about is with reference to the means of the two conditions. So really, this null hypothesis that the slope is 0 is actually what the real hypothesis is that the difference between the two means is 0. So if I want to say my null hypothesis is that the mean of F1 is the same as the mean of F2, another way to write this is to say that the mean of, what did I write here? Right. The mean of, so let me write it like this. Mean of F2 minus the mean of F1 is 0, right? That could be just a reordering of the null hypothesis that I have here, just rewritten that. And so what you should notice here is that each of these means has a coefficient associated with it, right? There's a number 1 and a -1 here associated with each of the mean levels. These are going to be called weights in the hypothesis statement. Okay, so you will see how I use this in a moment, but in any case, this is how I'm going to write my null hypothesis with reference to the means of the two conditions. Okay, and this is the null hypothesis. This number 3 here, equation 3 is a null hypothesis being tested by the treatment contrast. Okay, this is not obvious when you look at this contrast coding output. There's a 0 for F1 and 1 for F2. Like, how can I know that? How can I know that this refers to the hypothesis shown in 3? This is what I'm going to explain in this lecture. Okay? All right, so the intercept in the treatment contrast coding expresses the null hypothesis that is generally of no interest at all to us, right? So in the treatment contrast coding, the intercept null hypothesis is that the mean of the baseline condition is 0. That is a completely uninteresting null hypothesis to test, but it's there for technical reasons. Okay, so formally the null hypothesis is as shown in 4. Okay, the weight for the mean for F2 is set to 0. So effectively the question is, what is the mean of F? The null hypothesis then becomes that the mean of F1 is 0. Okay, that's what the intercept tests. That's why we generally ignore the null hypothesis test of the intercept. Okay, because it's not really interesting. So as I mentioned earlier, and I'm repeating now, you can change the level orderings, and what that does is it makes F2 the baseline and F1 becomes the other condition then, and then what happens is all that will change is the meaning of the intercept will change. So the intercept's null hypothesis will become that the mu of F1 now is 0, and the slope's null hypothesis will be, right, so let's call this mu null hypothesis 0, null hypothesis 1 will be that the mean of F1 minus the mean of F2 is 0. So the order in which to do the subtraction has changed now as a function of the factor leveling, right? So which one is the baseline now? F2 is the baseline now. Okay. All right. So this is that was the treatment contrast. The sum contrast that I showed you earlier, when I discussed it, when I introduced it, I was using -1 and +1 weighting, right? But you can use 0.5 weighting as well. This is called effects coding. It has a very minor effect on the intercepts. I will explain this in a bit, but I could have used +1 -1 coding or -1 +1 coding, but I'm using -0.5 plus 0.5 coding. And what I'm doing here is that for some contrasts, which we have seen before, okay, for some contrasts, I'm now setting it up so that one level, so the level F1, I think it was, has 0.5 coding, and the level F2 has -0.5. We'll just find out what it was. Okay, I've forgotten what the leveling was that I used just now. So now when I fit, I've set the contrast coding to be some contrast. Now I've changed it from treatment contrast, which is the default. So now what's going to happen is that when I fit the linear model and look at the output, what I get is the following. So I don't know if you can see this, but the intercept has the mean of the first condition. Remember what the table was? Is it here? Yeah. Oh no, sorry. Oh, sorry. So I'm talking about some contrast now. I'm confused here. So the grand mean of the data is 0.6, right? The grand mean is 0.6. And so in the sum contrast, what's going to happen is that when I fit my model with beta 0, beta 1, and then F as my predictor, right? This is my linear model now. With some coding, the intercept is now going to represent the grand mean. And you see that here. 0.6 is the grand mean. And the slope is now going to represent the deviation from the grand mean for each of the two conditions. Okay, so how do we write this down? So the intercept is going to represent the grand mean. That's what I'm showing you here. And the slope is effectively going to tell you the difference between the two conditions, right? This doesn't seem obvious when I say that the slope is actually representing the deviation from the grand mean. And now I'm telling you that the slope is telling me the difference between the two conditions. But actually those statements are both true. Okay, so this requires a little bit of simple algebra. I want you to think about this. I won't reveal this yet. You can work it out, or maybe we can discuss it in the Zoom lecture or something, right? Okay, so basically the sum contrast is going to express the null hypothesis that the difference in means between the two factor levels is 0. And so formally, the null hypothesis can be written as shown in equation 7. I could have also written this null hypothesis like this, by the way. Nothing much changes, right? These are just weightings. I could have written -0.5 mu f1 and then plus 0.5 mu f2. Okay, so please don't be confused by this. That why am I sometimes using -0.5 plus 0.5 and -1 plus 1? These are weightings that actually have no impact on how I state the null hypothesis. They will have an impact on the magnitude of the slope, and that will tell us something about so what you will see in a moment is that when I use plus 0.5 minus 0.5 contrast coding, what that will do is that the slope that I will get, the beta 1 estimate that I will get, this beta 1 estimate that I will get with 0.5 plus minus 0.5 coding, this will tell me the exact difference between the two conditions. This will give me the exact difference between the two conditions that I want to compare. Okay, so the difference between the two conditions in this case, I think, is what was it? Let's go back and look at these two guys, right? So there's 0.8 and 0.4. What's the difference between these two conditions? It's 0.4, okay? So with plus 0.5 minus 0.5 coding, what will happen is that the magnitude of the beta 1 will be 0.4, right? But if I set the contrast coding to plus 1 minus 1, the magnitude of this this beta 1 will be scaled, okay? And so you will see once you start doing the exercises that I give you what happens here. I don't want to reveal this. I want to leave this as slightly as a mystery right now. But all I'm saying here, to give you a hint to what's coming, is that we're just scaling the hypothesis test, right, by changing the weightings from 0.5 to plus 1. Okay, I could have used plus 2 minus 2, right? It's just changing the weighting. The hypothesis doesn't change. The null hypothesis remains exactly the same, right? So this null hypothesis I could have written with minus 0.5 mu f1 plus 0.5 mu f2 equal to 0, or I could have replaced these numbers with minus 10 plus 10, right? The null hypothesis is not changing here because I'm just scaling it, right? Okay, so but it does have an effect on what the magnitude of the beta 1 is, and you will see that in the exercises. Anyhow, so coming back, sorry for the digression, right? But coming back to our coding of plus 0.5 minus 0.5, okay? So in the case of the intercept in some contrast, as I said, the null hypothesis is that the grand mean is 0 of the two conditions, right? And so we can write the null hypothesis in any of these ways that I've shown here in equation 8. Okay. So the key difference between the treatment contrast and the sum contrast is the following, right? So the only difference between them is that they change the way that you parameterize the hypotheses, and the reparameterization of the model changes the underlying hypotheses that you're testing. In the treatment contrast, when you have two conditions, for example, the intercept is reflecting the hypothesis test that the mean of the baseline condition is 0, whereas in the sum contrast, the intercept is reflecting the hypothesis that the grand mean is 0, right? And the slope in both the treatment and the sum contrast is actually reflecting the same hypothesis, namely, is the difference between the two conditions 0 or not? Okay, so this may not seem obvious right now, but you will see that it is actually obvious later on, okay, when you do a little bit of work on this. So that was the two condition case. In the two condition case, we have only two choices. We can either use a treatment contrast or a sum contrast, right? So that's what I showed you. As I mentioned some lectures ago, in this course and in the research that I do, I will always use sum contrast coding, right? Why? Well, one of the reasons is that the sum contrast basically centers the predictors, and this makes the intercept easier to interpret in many situations, right? And there are other technical reasons for using sum contrast coding. I hinted at this at the technical reason when I gave you the formal matrix formulation of the linear model, and I asked you to compute towards the end of the lecture. I asked you to compute the correlation between the two estimators of beta 0 and beta 1. And I showed you that when you center the predictor, the correlation between the two estimators is essentially 0, right? And I gave you a little exercise where you do not center the predictor, and then when you compute the correlation, you will find that the correlation is something like 0.9 or something like that between the two estimators, right? So one advantage of the sum contrast coding is that it allows you to carry out orthogonal comparisons between two estimators that are uncorrelated to each other. So you can ask independent questions from the data, right? So this is a very useful thing when you have multiple conditions and you want to be able to ask whether each pairs of effects is different from each other and you have multiple pairs of these effects that you're comparing, these become orthogonal questions when you have a centered coding, some contrast coding. That's why it's so valuable for us in hypothesis testing. And this, you will see more details about this when you look at the output of a linear mixed model, where the correlations between the fixed effects are also shown as part of the output. You will see the correlations changing depending on whether you have some contrast coding or treatment contrast coding. Okay, you will see all this coming up. Okay. All right. So now I want to talk about a more interesting, a more complex design. A 3-condition case. Okay, so now I have 3 conditions and the underlying means for the 3 conditions are shown here. I have because I have 3 conditions, I'm going to set up the means as a 3x1 matrix, right? So this will look like this: 500, 450 and 400, right? So 3 rows and 1 column. And I've generated some new simulated data with the 3 levels of a factor in between subject design. And I've done some cleaning up of the factor names. What I'm simulating here is a situation where we have three types of frequencies, okay, word frequencies that we are testing. You can have low, medium and high frequency words, and we can record the mean reading time from each subject for each of these 3 frequency levels, right? So what one would expect is that you would have a data frame with low, medium and high as the 3 levels of frequency. You have the subject ID and then you have the dependent variable, and you can look at this as a table and you see that the true underlying means are shown here, and there are standard deviations, etc., for each of the levels, and I can compute standard errors, etc., as I showed you earlier. Okay, you could also visualize this graphically, and so what we have now is a simulated experiment where we got factor f, which is frequency being manipulated, and on the y-axis here we have the mean reading times with plus minus 1 standard error, right? And so what you can see when you plot this simulated data is that the low frequency words take the longest to read, the medium frequency words take an intermediate amount of time to read, and the high frequency words are read the fastest. This is the classic result in reading, right? You can replicate this easily if you do experiments. One of the most solid experimental results out there. So this is a very realistic situation now that we are looking at. And so one typical thing you would do in a 3-condition design like this is that you would want to compare this condition with this condition and second condition with a third condition, right? Once you've done those 2 comparisons, the third comparisons of low compared to high is redundant. Okay, so when you have 3 conditions, you just do 2 comparisons. Okay, so how do we proceed now? We can fit a linear model using the AOV function. So this is just the syntax that's used for the AOV function. You're not familiar with the syntax because I've always shown you the ANOVA with the linear model. So I've redone that analysis using the linear model and put the wrapper function AOV around it to do the ANOVA calculation. It gives you exactly the same thing, right? So what we're seeing here is an ANOVA done with a factor with 3 levels. So all that this ANOVA tells us is that there is some difference between those 3 conditions, but it doesn't tell us which difference it is. Is low slower than medium, but there's no difference between medium and high. Okay, that is not known to us when we do the analysis of variance. So typically what people will do is this is how I was also taught how to do data analysis. First do the analysis of variance when you have multiple conditions. If you find any significant effect, then you do your so-called post hoc t-tests. Okay, that's how people are taught to do these analyses. But this is I think that this approach is misguided, and I suspect that this approach was taken in the era where you did not have computers, and all the ANOVA calculations and t-test calculations had to be done literally by hand. And so if you have a multiple condition experiment, maybe in those days, I'm talking about 1800s or 1900s, sorry, in the 1900s, In those days, because one didn't have computers, you don't want to waste effort doing pairwise comparisons, so maybe you do one omnibus ANOVA is what they call it. So this is an omnibus ANOVA that I've just done, and if you know that there is some significant difference, then you go through the extra effort of doing those t-tests. I suspect that this is what must have happened, and this is why we ended up in this unfortunate situation that people first do an omnibus ANOVA and then they do the pairwise test if there is any significant effect in the omnibus ANOVA. Look, in the 21st century, this is nonsensical. Okay, so you've done a 2x2 experiment, you have some hypotheses, just test them. You don't need to go through all this drama of doing an omnibus ANOVA first. Okay, so people are shocked when I say this, because we are taught to do statistics in a mechanical way, right? We are told that here is the procedure, you just cut along the dotted line and you will get your answer. Okay, I want you to just throw away that way of thinking and just try to use common sense when you're trying to, work on your problems, right? Don't care about how people have done it in the past. And in fact, this is not something that I'm saying. I mean, there are famous textbooks by there's a famous psychologist called Hayes. In the 1970s, he wrote a textbook in which he actually pointed this out, and many other scientists, psychologists and other researchers have pointed out that, look guys, let's not do this ridiculous omnibus and then do the pairwise test. Let's just go and do the hypothesis test that you want to do. This is what contrast coding is good for. It allows you to directly answer your research question without this two-step procedure, which is just a historical artifact, has no relevance in today's world. Okay. Alright, so now for the three-factor level, how do I proceed with my data analysis? I'm going to define three hypotheses. Okay, one for the intercept and two for the other two slopes that I will get. Remember that I have three conditions, and I said that I'm going to do two comparisons, and what that implies is that I'm going to have a linear model with an intercept and two slopes. So I'm going to define a null hypothesis for this one, and this one. Okay, so that's where we are going now. So the null hypothesis for the intercept is going to be that the grand mean is 0. Okay, this is just like we had done earlier. The null hypothesis for the first slope will be that the first condition's mean is equal to the grand mean. The second hypothesis for the slope would be that the second condition's mean is equal to the grand mean. Okay, so now these are the three hypotheses I've set up for a three-factor level that I'm working with, and now I can rewrite the hypothesis for the intercept, which I'm calling H0, 0. I'm going to rewrite that by reweighting the three means. Okay, so remember that my hypothesis was something like mu1 plus mu2 plus mu3. Sorry, my handwriting is so terrible. Is equal to, so the average of these is equal to 0. I can just rewrite this by taking this denominator and putting it next to each of the means, right? The reason I'm doing that is that I'm representing the null hypothesis in terms of the weightings of each of the means involved in the null hypothesis. Okay, so these weights now start to become important for us. Okay, remember I was harping on and on about the +1 -1 and +0.5 -0.5 coding in the sum contrasts. Now you're seeing the weighting again in the null hypothesis here. Okay, for the second hypothesis I can do the same thing. My second hypothesis was that mu1 is equal to the grand mean of the three conditions, right? So I can rewrite this. So let me just do some math here for you. Where is my have I lost my OneNote here? Let me just bring it up. Right, so here we go. So can you see this? Yes. Right, so what I'm going to do now is I'm saying my null hypothesis is that mu1 is equal to the grand mean, which is what is that? Mu1 plus mu2 plus mu3 divided by 3. Okay, so I can now rewrite this as mu1 is equal to 1/3 mu1 plus 1/3 mu2 plus 1/3 mu3, right? When I do that, when I write it like this, I can now rearrange this a little bit to get my weights lined up, you know, in terms of mu1, mu2 and mu3. So how will I do that? So mu1 minus 1/3 mu1, right, minus 1/3 mu2 minus 1/3 mu3 is equal to 0. Is just a restatement of this thing here. Now mu1 minus 1/3 mu1 will give me 2/3 mu1 minus 1/3 mu2 minus 1/3 mu3, right? So I'm just rearranging all this, and so what this gives me now is a weighting 2/3 minus 1/3 and minus 1/3 for the three means. I've got this weighting that corresponds to the null hypothesis test that I had just set up. Okay, this H01 here. Okay, so this is the new weighting that I have defined for the three means. Okay, so these weights become very important for us in specifying the null hypothesis, right? Similarly, for H02, when I have a null hypothesis which states that mu2 is equal to the grand mean, if I rearrange just like I did earlier, now I'm not going to do this again, but if I rearrange everything, then the weights that I get, if I order them by the different means, are these three weights here, right? So minus 1/3 plus 2/3 and minus 1/3, right? These are the weights for the third hypothesis that I've set up. Okay, so really what I've got is, if I just concentrate on the weights that I have in the three hypotheses, I can write down something that I'm going to call the hypothesis matrix. This is not a standard statistical term, but I'm just making this up now. Okay, so this hypothesis matrix is now going to represent the weights for us so this is the weights for the first hypothesis test for the intercept. Here's the one for the second one, and here's this third one. Okay, so now I've written it out as a matrix, and so the reason I'm doing this is that I can now compute. Remember, in the matrix algebra version of the linear model, I had talked about the inverse of a matrix, right? So I had often done things like this, that I had an inverse of a particular matrix, and I would write it like this. So there is a function in R called the generalized inverse, so G_inv, right, that takes a matrix and inverts it. Okay, so what we have done here is that we've written another function called G_inv2, which provides a pretty printed version of the inverse of a matrix. Okay, so the relevance of that inverse procedure is that we are going to take this so-called hypothesis matrix and we are going to invert it using the G_inv function. Okay, and when we invert that function, we are going to get the contrast matrix. I think this is a moment of enlightenment for us, because like what we see here is a deep connection between the underlying weights of the hypotheses that we specified and the contrast coding that goes into the linear model. These two things are linked by the generalized inverse function. Okay, you can go back and forth between the contrast matrix and the hypothesis matrix by just running through the generalized inverse, right? So if I take the hypothesis matrix and compute the generalized inverse using my pretty printing function, what that gives me is the sum contrast coding for the three levels. Oh no, sorry, not the sum contrast coding, but the contrast coding that I need to express those three hypotheses in as a contrast matrix, right? So if you now look at the built-in function, the contrast sum function, and print out the output with the three levels, what you will notice is that the output of the contrast sum function for the three levels corresponds exactly to the output. So these two columns here correspond exactly to the contrast sum 3 output, right? If you compare those two, right, compare this thing, sorry, I wanted to draw this whole thing here. If you compare this thing, this with this, you'll see that the generalized inverse of the hypothesis matrix corresponds to the output of the contrast sum function with 3 levels. Okay, so what this shows us is that the 3 hypotheses that we set up and the weights that we set up in the 3 hypotheses, they are actually determining the contrast coding that we need to answer those hypotheses. So the practical consequence of this is that when you set up your 3 condition design and you have certain hypotheses you want to test, you can write down the hypotheses, extract the weights of each of the hypotheses, create a matrix of the weights, run it through the ginf function, and you will get the contrast matrix that you need to test those hypotheses. That is the amazing thing here, right? I think this is a really stunning fact. If you encounter it for the first time, is really an amazing fact that you can now translate your hypotheses to a particular contrast matrix. Okay, so what I've done here is that I've taken the factor column in my simulated data, and I've taken the second and third columns of the the inverted hypothesis matrix, and I plugged it into the contrast function there. And what I've done in effect is that I have ensured that those hypotheses that I had set up are now going to be tested. Now I want to point out to you that I'm only using the second and third columns of my inverted hypothesis matrix. Why is that? The reason is that the first column is always going to be plus ones, because it's always going to involve the intercept. Okay, so if you remember when I talked about the matrix formulation of the linear model, okay, so that's why it was so important to discuss the matrix formulation first, right? So remember, my matrix formulation was y is equal to x beta plus epsilon. And so if my underlying model has 2 parameters, beta 0 and beta 1, what's going to happen is that this design matrix will have the following property. The first column will always have 1s in them, and the second column will have the x values, right? And that's how we end up, if you remember when I unpacked the matrix formulation, that's how we end up with the intercept and then the slope in the linear models, right? So this first column is always going to be 1s, and that's why when I do this inversion, when I invert the hypothesis matrix, the first column is always going to be 1s, and therefore when I'm doing this contrast coding, the contrast coding is with reference to the condition levels. That means the slopes, right? And that's why we're going to ignore the intercept completely when we specify the contrast coding. We're only going to focus on this part of the contrast coding because that's the part that references the slopes, right? So that's why I've got the second and third columns only here, right? So the syntax that I'm using here is not the standard syntax, because standardly what you would do is you would say contrast sum with levels 3, and you would plug that into the contrast function as shown here. Okay, it's exactly, these two things are exactly the same here. Okay. All right, so now I've defined my sum contrast coding for 3 factor levels. Really what I'm doing now is that I've got these conditions like, what is it, low, medium, and high are my 3 factor levels. I'm gonna do one comparison like this and another comparison like this of these 2 conditions. All right, that's what's gonna happen now, right? All right, so yeah, so I'm just reminding you here of the matrix formulation. Now the important thing that I want to remind you of is that I had shown you in the matrix formulation lecture that the beta hats are actually estimated from using this equation. Now the interesting thing is that the hypothesis matrix, right, is this x plus that I had shown you in the lecture, this part here. Okay, this corresponds to the hypothesis matrix, and if I take the generalized inverse of this part of the matrix statement here, I get the contrast matrix. Right, so I get the design matrix that I'm showing you here. Okay, so this is why understanding the matrix formulation of the linear model is kind of important, because you understand what the relationship is between the hypothesis matrix and the contrast or the design matrix here, right? So the generalized inverse of the hypothesis matrix is actually this part of the equation that computes the beta hats. Okay, And really what it's doing is that when I say x plus, right, this x plus here and y, this x plus matrix, which actually determines the hypothesis, is actually reflecting the hypotheses, underlyingly. This x plus matrix is relating the observed values to the beta hats, right? And so of course I'm not spelling out the details here, but at least I want you to appreciate that there is the design matrix which will contain the contrast coding, and then there is this x plus matrix which actually reflects the hypotheses that we are talking about. Okay, all right, it's really deep if you think about it, but it takes some time to get used to the fact that there is this deep result that relates the x plus matrix with the contrast coding in the design matrix or the model matrix. Okay, all right, so I have now set up my model with the appropriate contrast coding, and I can now print out the output. And what I see when I print out this output is that I get the two hypotheses being tested in the slopes here, right? So is something wrong here? We'll have to look into this. Okay, so maybe there's some mistake here. I will look into this and issue a correction later on if there is a problem. Maybe I'll give a homework assignment involving the 3-condition case, so we can work through it ourselves. You can work through it yourselves and get some idea of what's going on here. Okay, so but what this output should have shown is the two hypotheses. I'm just surprised that the difference between the grand mean and the mu2 is so small. Could that be true? Now I want to know. I'm getting confused here, but maybe I've made some mistakes somewhere, and we will look at this in a moment. Sorry about that. So what were my 3 condition levels? Sorry, let me just do this. Okay, my hypothesis for the second case was that mu2 is equal to the grand mean. Okay, so what was the grand mean? Let's take a look. Right, so my grand mean is the mean of 500, 450 and 400. So the grand mean is 450, right? And right, and so the mean for the second condition is also 450, right? And therefore I'm testing the null hypothesis that the mean of the second condition is different from the grand mean, and we can see that it's actually essentially 0, right? There is no difference, so there is no mistake here. This is correct, right? So the output that I'm seeing here is correct, so I'm very relieved about that I didn't make some mistake here. This difference is actually reflecting exactly what we intended to ask, which is the difference between the second condition's mean and the grand mean different? And so you're not seeing exactly 0 here because of some random variability in the numbers that were generated. When you're simulating data, there will be some deviation around the exact numbers, so the mean calculation won't be exactly 0, but it's close to 0, right? So this is all good, we are fine. Okay, so what I have shown you here is the 3-condition case. You define your hypotheses. Okay, so this is the procedure. We write down our hypotheses for the intercept and the 2 slopes, extract the weights of the 3 hypotheses, write them in the hypothesis matrix, invert that hypothesis matrix, right? Get the generalized matrix inverse of the hypothesis matrix, and then assign the generalized inverse, all the columns except the intercept column, assign those to the contrasts function, for the relevant factor. You could use the contra sum built-in function contra dot sum for 3 levels here, and then you run the linear model and it does the appropriate hypothesis tests. That is pretty cool, I think, right? It relates the hypothesis test to your your linear modeling contrast coding, right? So the amazing thing that we have achieved here is that we are no longer doing an omnibus ANOVA and then 2 pairwise t-tests. Okay, we are just fitting a single model that answers all the questions in one shot, and we are finished. So the practical consequence will be when we are actually doing research analyses, data analyses, we are not going to go through this drama of multiple analyses. We're going to fit all our hypotheses or test all our hypotheses in a single shot in a single model. That's going to be how we proceed. Okay. So that's the payoff of learning this whole approach of contrast coding. Alright, so you can also set up a different contrast. So there are many different contrasts available. I'm introducing a third one now, apart from some contrast. You can set up a contrast where you want to compare, let's say I have the low, medium, and high. So this is what I had talked about in the beginning when I was introducing these 3 conditions. A typical comparison is not the sum contrasts, right? The ones I just showed you, but a typical comparison could be between these 2 pairs of conditions, right? So this is called as repeated differences or sliding contrast, right? So you can use a sliding differences function, the contrastive function, to encode these comparisons. Okay, so what this does is that it compares medium to low and high to low frequency. You can check what those numbers should be when you by taking the means from each of the levels. So this is the first comparison, this is the second comparison, and indeed when I specify using the contrastive function instead of using contrasum like I had done earlier, I had used contrasum to test those hypotheses that I told you about. Now I'm testing different hypotheses. Okay, and the hypotheses I'm testing are these repeated differences, medium versus low and high versus medium, right? So for that I would use this contrastive function, and once I specify that contrast coding for the contrast matrix, I will get exactly the same differences, right? These 2 differences is exactly what I'll get out of the model as well. Okay, so the point here is that you can use the sum coding, contrasum coding function or the contrastive function to answer different research questions. For 3 conditions, I mean, there's a limit to the type of questions you can ask. You can either ask this repeated differences type of question, or you can ask the sum contrast type of question, right? So those are the 2 kinds of hypotheses you can set up and ask. Alright, so that was the 3 condition case, and now hopefully you have a good sense of the differences between the treatment, sum, and the repeated differences contrast. Of course, the repeated differences contrast is only relevant when you have more than 2 conditions. Okay, the repeated differences contrast and the sum contrast will give you exactly the same contrast coding and hypotheses if you have 2 levels. Okay, so if you have contra sdiff 2 and contra sum 2, these should give you exactly the same thing. So let me see, maybe I'm going to embarrass myself now and get this wrong, but let me just check this for you. Okay, so contra sdiff 2 is giving you that plus 0.5 minus 0.5 coding that I had shown you earlier when I was setting up the pairwise contrast by hand, and contrast sum is setting up the plus 1 minus 1 coding, right, instead of the plus 0.5 minus 0.5 coding. I just want to remind you that these 2 things are exactly the same. It's just the weighting that is changing, right? I'm just changing the weights of the thing. I'm scaling the weights, but basically they're both giving you the same hypothesis test when you have 2 conditions. When you have 3 conditions, things get interesting because the type of comparisons you can do are actually different. The kind of hypotheses you can set up are different, as I showed you, right? Therefore, it is important to think about what your research question is before you actually start doing the data analysis. Don't just play around with different contrast codings to see which one comes out significant. Okay, please, that is exactly the kind of thing that lands us in the kind of mess that we are in generally with all this reproducibility crisis and so on, right? We want to define our hypotheses in advance of collecting the data. We define the contrast coding in advance of collecting the data, and then we run that analysis. Of course, you can explore the data afterwards and do whatever you like as an exploratory step. That's how you discover new things. But there is a difference between your planned analysis and the exploratory analysis. So these two things should be kept completely apart. Okay. All right. So now the last topic I want to cover in this lecture is the 2x2 factorial design. So this will be a very common situation here. So I've set up a situation where I have four conditions, right? Each of these has a certain mean, and I've set up a 2x2 between subjects design, 5 data points in each condition, and the factor levels are called A and B. So let me show you what this looks like. I've got two levels, A1, A2, and B1, B2, right? So I'm going to have to set up my data frame to reflect those levels, and I have the sample means and standard error, etc. all set up. Okay. So now you can graphically summarize this data, and this is how we typically report our results in papers as well, right? So what you're seeing is for factor level A is in the x-axis, and so the two levels are shown here for the two different levels of factor B. So these two means that you're seeing, this mean and this mean, they're coming from B1, right? Factor B1, level B1, and these ones are coming from B2, right? So what you can see is, if you just look at this figure, what you're seeing is an interaction between the two factors. Okay, so you could ask whether there's a main effect of factor A, right? What you're asking then is, take the average of this, two numbers, and find out if the difference between those two means is significantly different, right? So the average of these two numbers would be some number here, the average of these two numbers would be some number here. So I would be comparing, if I'm looking at the main effect of factor A, I'm trying to find out if these two means are different from each other. Okay, so I just want to undo this so that I can draw some more. Right, so similarly I can ask if there's a main, Right, so I can ask if there's a main effect of factor B, and that question can also be asked. And then what I would have to do is I would have to collapse over the different levels of factor A, then ask if there's a difference between factor B. The interaction is telling you whether there's a difference between the two differences, right? So if I look at the difference between A and B, this difference between these two conditions, I'll call it D1, and the difference between these two conditions, right, will be this magnitude here. I'll call that D2. The interaction is actually testing whether the difference between the two differences is 0 or not, right? D2 minus D1, is that equal to 0 or not? That's the null hypothesis being tested by the interaction. Okay, so really when you have a 2x2 factorial design, you're going to have a test for a main effect of the first factor, the main effect of the second factor, and the interaction between them. Okay, so let's do that. Okay, so if I run the AOV function and I compute the main effects and interactions, so this syntax here is actually really saying find out the effect of factor A, find out the effect of factor B, and then find out the interaction, which is written with a colon, of the two factors. Okay, the shortcut syntax for this kind of main effect and interaction is to just write A star B, because it just sort of is a shortcut syntax for that. Okay, so once you do this, what you get as an output of this ANOVA is the main effect of A, main effect of B, and the interaction, right? And you see that you see some F scores here, 5, 20, and 5, and they all seem to be significant, so something to get excited about. Okay, all right, so now the surprise is, you should be surprised now when I run the linear model version of this ANOVA and I do the same main effects and interaction analysis. So what will happen when I do this is that my t-scores don't actually match up with the f-scores that I have here. Remember that I told you sometime back that the t-score should be equal to, t-square is equal to f. right? So the t-values in the linear model should have been exactly the square of those t-values should have exactly been the f-scores here. You can now confirm, go back and confirm that that's not true here. Just look at these t-scores and take the square of those numbers and compare them to the f-scores you see here, and you'll see that they are not identical. So how come? What's going on is that here that what is happening here such that the ANOVA and the linear model, which I told you earlier are the same thing, are giving you completely different answers. It's mysterious. It's not mysterious because what's going on is that the linear model function by default will use treatment contrast coding unless you change it. ANOVA uses the sum contrast coding for the factor levels, and that's why you're seeing a discrepancy between the ANOVA f-scores and the t-values of the t-test. Okay, this discrepancy. Now ANOVA uses sum contrast. We can force the linear model to do that too, and once we do that, what we will find is all the t-values will now be exactly the same as the f-scores. That means t square will now be exactly the same as the f-scores, right? So you can see this now. I've recoded my factors, right, with contour sum for factor level A, for factor level B, and now when I run the linear model function and I look at the output of the linear model and I look at the t-scores, the intercept we can ignore, right, as I mentioned earlier, minus 2.2361 squared is going to be equal to, it's going to be equal to 5. Okay, I'm going to go out on a limb and say that. You can check this, okay? And minus 4.4721 squared is going to be equal to 20, right? Am I right about that? Yes. And this last one here, 2.2361 squared, is also going to be equal to 5. Okay, you can check this. Go ahead and check this in RStudio if you want, right? And so what you see now is that the contrast coding in ANOVA is always going to be sum contrasts. ANOVA internally changes that contrast coding. You don't even see that. The linear model uses the treatment contrast coding. You don't know that. I mean, it doesn't print out anything to tell you that. You're supposed to know this as a modeler, right? The software, our software actually expects you to know all this stuff, right? So you should always check what your contrast coding is when you're setting up your data analysis. Don't just plug in the data and run the code, because you'll end up with some contrast coding that may not be what you need. And to be honest, I very rarely use the treatment contrast coding in my research. I almost always use the sum contrast coding because of the centering issues that I mentioned earlier, right? All right, so that's the main story with contrast coding. I think with the knowledge that this lecture gives you, you're pretty much ready to do any kind of data analysis that you're interested in. There's only one contrast coding I didn't teach you about in this well, there's a couple I didn't teach you about in this lecture, but I'll leave you to discover those later on, right? If you read the paper that I've given out as an extra reading for this lecture, you will discover what the other contrast codings are that I didn't discuss. But really, the reason I didn't discuss them is that they are actually very they're just extensions of what I've discussed now. The baseline knowledge that you need to do contrast coding is now in place, and now in principle you're ready to do anything that you need to. Any research question that you have can now in principle be answered using contrast coding. Now I wanted to point you to a library that one of our students has prepared. It's called a package called Hyper. You can read the documentation on this. I won't walk you through this because I think you will understand this now once you read it, and I encourage you to read this documentation. What this package does is that it allows you to translate quite easily between the hypotheses that you set up and the contrast matrix that you will need. So you can use this package as a guide for designing your contrast matrix when you're doing your research. Okay, that's the practical use of this thing. Okay, so one final point I want to make in the last few slides is that in my own research, as I mentioned many times now, I like to keep the design simple. Even a 2 by 2 by 2 design is too much for me, okay? But sometimes I'm forced to use such designs when I'm, for example, exploring some ideas that some other people have proposed. I often end up in more complex designs than I would like. In general, I will always set up some contrasts, and another approach that I will take when I'm analyzing these data sets is might do nested contrasts. An example of nested contrast coding is discussed in this paper that I recently published with some of my students. And the source code for all the data and analyses are available here. It's a very large zip archive, so it's 9 gigabytes or something like that, so it'll take a while for you to download everything, but you can see the contrast coding that I use there and that we use there, and there we also use something called nested contrast, so you can see an example of that there. Okay, there are also other papers on my homepage where we have used nested contrast coding, so let me just quickly point you to those papers. If you go to my homepage under publications, you will see some papers, which all of these papers come with source code. So look at this first one by Serena Avetisian. In this paper, you can download the source code. When you click on the paper, you'll see the link to the source code. I should add it here also. I don't know why it's not here, but you will see some examples of some nested contrast coding here. Here is the paper I just mentioned where you have nested contrast coding. The code is available on this archive. You can download this zip archive containing all the code, right? And look at the contrast coding. There are some other examples where you will find the same kind of issues coming up and again, some data analyses that we have done. So, for example, let's see. Here is an interesting data set, right? The source code is available here. This is a data set with a 2 by 2 design, and here you can see the contrast coding that I used for the data analysis here. Okay. Another nice example would be where's the paper with 2 conditions? Yeah, so this paper is also worth reading, because in this paper, this also has source code and you can download it, right? So this paper actually has only 2 conditions. This is a beautiful experiment with only 2 conditions. So the only contrast that makes sense here would be the sum contrast. Okay, so that's a simple example. So these are papers that you can look at to see how real life data analyses are done, and this how I apply these approaches for my research. Okay, so one other thing I want to mention is that I never actually use these built-in functions, the contra sdiff, contra sum, and so on. I never use them. What I actually do is I define my own contrast coding columns for the design matrix by hand. Okay, so I'll give you an example of why this is relevant and why I do this. Okay, so what I'm going to show you now is a data set from a Persian self-paced reading experiment that we had done. This is a 2 by 2 factorial design, and the 2 levels are distance. So there are 2 distance levels, right? Call them A and B, and 2 predictability levels, right? So I call this DA, DB, and 2 predictability levels, which I call PA, PB. Okay, so this is a simple 2 by 2 design, and so the distance manipulation has short and long conditions, and I have recoded those by hand. I created a column called dist. Okay, so the column with the words long and short is called distance, but I created a new column with plus minus 1 coding done by hand, right, using a command I will just show you. And so I have recoded those long and short conditions as +1 -1. Instead of using the contra sdiff function and plugging it into the contrast function, what I've done is that I've defined the contrast coding by hand. Okay. Similarly, for predictability, I've got predictable and unpredictable as the two levels. I've coded those as +1 and -1. Okay, so I could have used contra sum, you know, in the way that I've taught you, and fit my linear mixed model. This is a repeated measures data set, so I'm fitting a linear mixed model, and so I'm fitting a maximal linear model, which you may not know, you don't know what I'm talking about here, but you will see later on that when I fit this linear model, I get some warnings which I'm going to ignore, but what happens in this linear model is that it prints out some correlations which it should not be printing out. It should not even be computing those correlations, right? So that's what I've written here, that these correlations should not have been computed. These end up getting computed for some reason that I don't understand when you define the contrasts using the contrast function, you know. But if I define the contrasts using my hand-coded vectors, you know, these are my vectors that I created, and I fit the model using these vectors. If I fit the same linear mixed model, I'm not the model should not be computing any correlations, and indeed what we see is that the correlations are not being computed as expected. Okay, so you will understand this point better once you actually look at the linear mixed models lecture. But this is the reason why I don't use this contra sum function. It has some weird behavior in the linear mixed models, right? Now the good news is that you can continue to use the contra estim function because it's not harmful in any sense. It doesn't actually have any impact on the final analyses, but it's for me it's very disturbing to see correlations in the output when I'm expecting none to be estimated, right? So I don't really like that, and so that's why I define my own contrasts by hand. And personally, I would encourage you to define your contrasts by hand once you've figured out what your contrast coding is going to be. Okay, so we'll have exercises on this later on. Alright, so now this was just an introduction to contrast coding. We have written a paper on contrast coding that you should read. It's a very long paper. It will take a long time to understand it. I don't expect you to read it during this course, but I expect you to read it at some point in your life when you want to have a more advanced understanding of contrast coding. Okay.